Hi, I'm Abby Castañeda, and this is the physics of curved balls. In previous units, we learned about how the force of gravity causes the vertical curve we see in projectile motion. However, in real life, objects in the air move not only vertically, but horizontally as well. In most sports, such as baseball, golf, tennis, and soccer, players create spin on the ball to manipulate the direction it's going in. But how does adding spin to the ball make its path curve? When a cylindrical or spherical object is moving with spin through the air, the magnetostatic force pulls it off of its intended projectile path in a direction perpendicular to its original course. At its core, the Magnus effect is created by differences in pressure on either side of the spinning object, and the higher pressure zone ultimately pushes the object to curve towards the area of lower pressure. So, how does the spin relate to the formation of different pressure zones? Let's take a look. This is Bernoulli's equation, one of the fundamental equations in fluid dynamics. It states that the total sum of pressure at any 2 points along a streamline is constant. In the equation, the first term represents static pressure P. The second term represents the kinetic energy in air, which creates dynamic air pressure. The third term represents gravity's impact on air pressure, depending on the altitude. Bernoulli's equation is basically the energy conservation equation modified to show the conservation of pressure along a streamline. It seems complicated, but the main point is that total pressure is conserved. So in two different areas of the same streamline, the sum of different forms of pressure will always be equal. Let's now apply Bernoulli's equation to the scenario of the spinning soccer ball. We can look at the air in the direction resisting the ball's motion as one constant streamline of air. The 2 points we are comparing along the streamline are on opposite sides of the ball. There's practically no change in altitude between these 2 points, so we can cancel the third term in Bernoulli's equation that accounts for changes in altitude. Because the ball is spinning, on one side of it, it's actually going with the flow of the streamline, which increases the velocity of the airflow going around that side. On the other side of the ball, the spin goes opposite to the direction of the airflow. So the air faces resistance in its attempt to push past the obstacle of the ball, and it has a slower velocity in that zone. So spin on the ball can either help guide the airstream, which happens for stream B in this diagram, or interfere with it like shown in stream A. We can assume that the airstreams start out going with the same initial pressure and velocity, and then write a Bernoulli's equation for both airstreams, airstream A and airstream B. Point 1 in both Bernoulli's equations will be before the air reaches the ball, and point 2 will be as the air is flowing past the ball. The velocity v2a, where the airflow has to go against the direction of the spin, is slowed down from the original velocity. Meanwhile, the velocity of airflow v2b is going in the same direction as the ball spin, so at point 2, for airstream B, it's actually going faster because the spin of the ball is supplementing the airflow. We will now subtract both equations. The left side of the equations will subtract to 0 because we assume the total initial pressures to be the same for both airstreams. And with a little bit of rearranging, the right-hand side could come to look like this. What this equation ends up saying is that the difference between velocities in the opposite side streamlines leads to the difference in static pressures. And since we know that the velocity of zone B in our example was higher, using our equation, that would mean that the pressure in zone B would have to be lower. This is Bernoulli's principle, which states that places where fluid flows at a higher velocity have lower air pressure. Let's recap. We see the Magnus effect in action when a ball curves in a particular direction without a visible force acting on it. The explanation behind this effect is that the spin put on the ball causes one side of the ball to propel airflow past it, and the other side of the ball to spin in the opposite direction of the air and slow it down. Due to Bernoulli's principle of pressure conservation, as we've discovered, the fact that air moves faster on one side of the ball than the other creates an imbalance in static pressure zones. Now, you might ask yourself, if total air pressure is conserved, then why the heck are we saying that there's a pressure imbalance? Why are we saying that the ball is only going to move because of static air pressure instead of dynamic air pressure or total air pressure? Well, that's because dynamic air pressure has more to do with the velocity and kinetic energy of the air, and it's not acting directly onto the ball. However, static air pressure is directly related to the force that's applied onto the surface of the ball, and that's what makes it curve, not the dynamic air pressure. Finally, the higher static air pressure on the side of the ball spinning opposite to the airflow acts as the force pushing the ball off course and towards the direction where the air pressure has been lowered. This ultimately results in a curved path of the ball.